We consider here a fourth order example of a differential equation with constant coefficients that is homogeneous, and we're going to tackle it using all the skills that we've built up so far. First step, because it fits this categorization of linear, constant coefficients, homogeneous, we're going to make our assumption that the y is equal to some exponential power. That's going to give us the characteristic equation of r to the fourth minus 8r cubed 26r squared minus 40r plus 25 has to equal 0. Now again, this is a fourth degree polynomial. It can be hard to solve. We could try guessing and checking, but someone thoughtfully gave us a hint before this. So let's just do a little aside here. Well, if we do r squared minus 4r plus 5 times itself, that's going to give us r to the fourth. Looking for r cubed terms, we'll have negative 4r cubed minus another negative 4. That'll be negative 8r cubed. Hey, you can see where this is going, can't we? We'll have plus 5r squared plus 16 plus another 5. Hey, that sounds like 26r squareds. And not too surprisingly, if you work through the rest of it, you'll get exactly the form that we had before. So what does that tell us? For this particular scenario, we can easily factor this as r squared minus 4r plus 5 all squared equals 0. Now in practice, how would you do this? I would probably use software to find the roots of this. On a test scenario, we would give you these hints as necessary. Either the roots will be very simple, like 1 or 2 or 0, or we'll have something nice like this to guide your way. Well, this is not trivial to factor. Why don't we use the quadratic equation here to help us out? We'll have negative 4 plus or minus the square root of 16 minus 4 times 5 times 1 all over 2 times 1. That's going to be 4 plus or minus 16 minus 20 is minus 4. That's going to be 2 plus or minus, we can bring the 4 out. It'll be the square root of 4 times the square root of 1 times the square root of negative 1, my apologies. And that's going to be 2 plus or minus square root of negative 1. All right. And that is all squared. So what we're going to have are these values of r, each with multiplicity 2. If we just found the roots of this without the squared term, then we would have gotten these roots. But because they're squared, we get each of these roots twice. Now, does that complicate our life? Surprisingly, not so much. This is a complex pair of roots. This is our a. There's a 1 hiding here that we can't see. That's our b. So our general solution, we can just write it down immediately, will be some coefficient times e to the 2x cos of 1, which I'll just write it as cos of x, plus c2 e to the 2x sine of x. That's for the pair here. We get 2 solutions and we're off to the races. Now we note that we have the multiplicity 2, so what we'd like to do is ideally use the same values again, e to the 2x cos of x and c4 e to the 2x sine of x. However, those would not be linearly independent. We need them to be linearly independent. And how do we accomplish that? Well, just like when we had repeated real roots, we slide in a multiplier of x in front of both of these. So whenever we have this case of a duplicated root, and we need to generate 2 functions that are similar but not identical, and certainly not linearly dependent, then we just slide in this x factor here, and the same thing for the sine solution, and that'll give us 4 linearly independent solutions that match the r values that we found earlier.